Sweet. Thanks for joining us, guys. I think we're about to get started. So my name is Alejandro. I'm from a company called Agnostic, our main product being Covalent. Just a show of hands, does anyone know what workflows are? Does anybody play with workflows? Okay, not many people. Okay, sounds good. So yeah, thank you so much for the iQuHACK team for organizing everything. It's been great. IBM Quantum for allowing us access to their quantum computer, which we'll be using for our challenge and a little bit for this tutorial as well. So getting started here. So this is also our team. If you have any questions throughout the challenge or any questions in general about Covalent, please feel free to reach out to us. So I'm an engineering manager at Covalent, and we'll be talking about kind of what workflows are. So you probably worked with workflows before. They're pretty much just any set of automated tasks that you can run. So it could be like a one-off script, like a Python script converting like your, I don't know, some sort of files to another file. You can do simulations. You can compute results. So if you ever done any kind of computational science courses, you do simulations. So which we call kind of experiments. You can also do more data kind of experiments like transform data. Typically it's like large amounts of data where, in practice where workflows are used, but you can compute results. You can also, act on the data. And, there's other things, any sort of DAG, any sort of things that are like kind of a graph of dependent tasks you can kind of think of as a workflow. So you can also have, like, if you worked with Terraform, also kind of creating infrastructure, that's also a workflow. So really anything you want to automate. But modern computational workflows are quite complicated. Like if you want to do something practical, like, do a large scale simulation, you're going to need to do, on-prem, HPC, high performance compute clusters. You might want to use the cloud, and sometimes you want to use a combination of these. And typically doing that is kind of complicated. How to get result back from your supercomputer cluster, or maybe even use quantum. How to kind of mix and match all these different types of hardware resources can be quite challenging. So this is kind of one of the primary reasons we built Covalent, so that this heterogeneous computing is actually a lot simpler. So right now we kind of have, like, even, using GPUs, CPUs, TPUs, or quantum computers, you, as a developer, you shouldn't really have to think about all these different sorts of hardware solutions, how you're going to run them, which compute environments. You should just really be able to write your code and then have the hardware resources do its thing under the hood. So this is kind of, so Covalent is an open source Python library, but we not only do we support Python, we support other languages as well, such as C. And yeah, so it's open source, so you can kind of take a look at our code as well, and it's free to use. So some of the features that Covalent offers is parallelization is one thing. So when you write your script and you have, getting results from, say a quantum computer or, a classical computer, what we typically do is we figure out the relationships between the tasks, and we run the ones that we can run in parallel whenever possible. So that's one of the benefits as well. Others are, the compute, the compute backend. We pretty much abstract that away completely. So you can use on-prem HPC. You can choose which compute backend has the hardware that you want. It could be a GPU, et cetera. But you can scale way beyond your local computer. So one of the questions is, like, why not just use your laptop? If you want to run a big enough simulation, what Covalent allows you to do is just write your code on your computer and then just send it off remotely, and we take care of the rest, essentially. Or we integrate with the various clouds in order to do that. So other things as well is like if you've ever run like a really large simulation that takes like, I don't know, like 20 hours to do, and then you have like one error in like one of your tasks, and you're like, oh, I gotta rerun this whole thing. So we are also in the roadmaps to also support the ability to, to essentially be able to rerun that simulation, just run that task that failed. So that's going to help quite a lot if you're doing a lot long running simulations. So we also have a really intuitive user interface. So this allows you to kind of version and let's share your code, share results with teammates, and you can really organize all those runs as well with our UI, which I'll show shortly. And it's also really useful just to diagnose if you're working again like with remote compute environments, you can see kind of get error back what happened with like the failed task in your remote environment. So this heterogeneity of like mixing and matching different compute backends is particularly how quantum is practical today. Like we still need to use classical and quantum together in order to have practical results. So this is one of the reasons why it's really beneficial to leverage Covalent in that way. We could also have like bursting requirements if you have like a really large task to do. Say like millions of tasks that you want to run, we can automatically scale depending on how much work you actually want to give it. And so it can scale pretty well. And it can scale back to 0 when you're not using it as well. So not only does this efficiency lead to faster results, it could also result in cost savings as well if you're doing a lot of these simulations. But using Covalent is actually quite simple. Like this is just an example of like a Python script, and really, we're training some model here, but all we really need to do is import Covalent, add some decorators to this code, and you could just use it as you would use the non-Covalent version. Just so Python and just run this script, and essentially it runs the workflow just with adding those decorators. So some of the concepts here are pretty simple. Like your Python functions, all you really need to do is add an electron decorator, and your entry point of your program is just called a lattice. And once you define these, you could just dispatch it and get your result back, just like you would with that regular script. So this is what our kind of UI looks like. It kind of determines kind of the relationships between the tasks. Again, there's kind of some parallelization done. You can look at your results, and you can also inspect the code in different parts of your application. So it's quite easy to use. I'll show the UI in more detail as we go along as well. But actually getting started with Covalent is quite simple. Like you just do, pip install it, you do Covalent start, and then you can just fire off your workflow. So it's actually quite simple to use. What makes Covalent particularly useful is that we have a massive plugin ecosystem, and we just by adding like these decorators, you can actually just send each particular task wherever you want to send it. So you can wrap it with, say, an EC2. You can send off just this task to create a new virtual machine on AWS, for example. So if you have like a really heavy task, you could just tell it to use like a really large VM in order to do that training, for example. So we have a lot of these executors, particularly some of the ones that I'm showing here are AWS executors. And so these executors, again, just allow you to essentially execute this task remotely. And so you can just do a pip install Covalent AWS plugins. And so this just installs the plugins, and you can just use them out of the box. So I'll be kind of doing a bit of a tutorial on how to use Covalent. I guess I can just go ahead and start, and I'll do questions after that tutorial. Let's see. Okay, so I'm going to start a Jupyter Notebook where I'll kind of go through some examples here. So, very cool. So, I mean, yeah, like getting started with Covalent, again, is quite simple. Let's just do pip install Covalent to get started with Covalent. Oh, I think the kernel is starting, so it's just taking a little bit. Okay, sweet, I think it's started. All right, sweet. Okay, there we go. So we installed Covalent there. So to start Covalent, we just do Covalent start. So let's wait till the server's up, and then you should be able to look at the UI. So if we look at the UI here, so this is where you'd see all your experiments or your simulations. So again, kind of in this example, so we have just like a standard Python, so some Python functions that, add, multiply, divide, and, let's just run this block. So we just get some results back from that. So this is just regular Python code. So we then go ahead and add some decorators, the electron decorator on our functions and the workflow, which kind of kicks off the workflow. So let's do that. And we see it here. We actually, now that we ran this block, we see that it actually did all the work, and I guess it was too quick, but yeah, there was some parallelization there as well, as it figured out kind of the dependencies between the tasks. So that's kind of like really all you need to do to get started with Covalent. It's quite simple. You could just add those decorators, turn your regular Python into a workflow. So I guess one of the things that's going to be particularly useful is, if you use AWS, some of the executor plugins that we have hook onto AWS. So if you have an AWS account, that'd be great. That's great. But if you don't, it's free to sign up, and you should have some credits, I think, out of the box to use. So I recommend to sign up for one if you don't already have one. So you can download the CLI as well. So that's going to be required for making sure that you're authenticated with AWS. And so I'll be kind of showing an example of how to use one of the AWS executors, which is AWS Batch. So with AWS Batch, you can pretty much create like a cluster of computers, and you can just send work to it. So this is quite useful, as you can have like, instance types that are like good for machine learning and have GPUs, some that are like just smaller for smaller tasks. And you can mix and match these instance types, but you can have a pool of computers. And so when you add this decorator to your task now, you can just send it off to that pool to get executed. So you can now, just from your laptop, handle a tremendous amount of scale, because you could just offload these tasks to this compute pool. So I'll kind of go with like a toy example of like training a machine learning model. So here I'm just going to train like a support vector machine. There's like an iris classifier, I think pretty standard. And so if I do that, I'll go ahead and do that, and we can see it in the UI, I think, executing. Okay, wait, I guess it's there. So yeah, so this is just kind of like a really toy example of how to use any sort of, you could just import your dependencies as usual and just add these decorators again. But when we want to use a batch, the batch executor, we'd need to just install that plugin. So it's, again, it's as easy as just doing a pip install. And so if you're in a notebook particularly, you might want to restart, because we might have to restart Covalent. Whenever you start install a plugin, you have to just restart Covalent. So we'll do that. Sweet. So typically when you're using these executors, you have to just, once you have to provision some resources in AWS in order to be able to, like your compute pool, you have to define which types of instance types you want. And I'll show how you can do this in a simplified manner, but you just need to provide some parameters here, like an S3 bucket to use, just a batch queue, etc. So I previously provisioned some of these this infrastructure, so I could just kind of copy and paste some of these values, but I'll kind of show how anybody can do it. Like you don't have to have expertise using AWS in order to use these. I'll give an example of how you can more easily use these in a second. So all we really need to do is instantiate this executor, and then we just add it to the Electron decorator in order to use this executor. So now that we've defined our executor here, given that this task is going to run remotely, we also need to define which dependencies this task has. So here we're going to use NumPy and scikit-learn. So when we actually do our training of the model, we're actually going to determine exactly which pip dependencies we're going to use. So, so this training now is going to happen remotely once I run this. So I guess let me run it. And so now we can kind of think about, like, if we're actually training a very, very large model, you can actually just offload it and to this compute pool. And so this is kind of like what I meant by you can scale way beyond your local computer and do tasks with like big scale. So this is just, so it sent it off to the to AWS to train. So it's undergoing the training process. And one of the things that you can do is you can inspect all the outputs of each of your functions in the UI. And so you should just be able to click through anything and see any of the arguments as well. So as that's kind of running, so it's probably going to come back sometime soon, but pretty shortly here. So again, as I mentioned, if you don't have expertise with AWS, I'll show kind of how you can kind of use some of the scripts that we have in order to boot up all these resources so that you don't have to go about doing that yourself. So one of the things that we offer is something called self-hosted Covalent, which pretty much allow you to like deploy Covalent in remotely in an AWS virtual machine. And along with that, we kind of create all the resources that you need, like the compute pools, et cetera, lambdas, and also bracket if you're using quantum. So this also facilitates that. So let's see, I think it's, yeah, sometimes when you kind of create your compute pools, you have to be careful because it might take a while for AWS to allocate the instance. So yeah, depending on which one you choose, it might be harder to allocate an instance. And so it kind of came back here and you can kind of see your score at the end. So this is particularly fitted for when you're using training like very large models, for example. So going about like self-hosted Covalent, what you'd need is to install Terraform. So there's a kind of link here to install Terraform. I've already gone about doing this. I think that there's so there I'll show kind of a quick video on how to go about this. So there's okay, so pretty much you could check out our Covalent Terraform repo, and this pretty much has all the instructions that you need. Really, it's just a matter of running a few different scripts. So you define some variables, which will become quite, I guess I'll show the repo first. So you kind of define some variables here, so such as like, just a prefix for all the resources that you're going to create, a public key, and for what instance types you want to use in that compute pool, for example. So so here you can kind of determine that. And going back to the video here, when you actually do the Terraform script, so which is actually just all you really do is just Terraform init, define these variables, and then you just do Terraform apply with these variables defined. And once you do that, so you do Terraform apply, it goes ahead and kind of creates all these resources. So this could take like a while. It could take up to like 10 minutes. That's why I'm kind of skipping through it here. So once all the resources are created, you'll pretty much have the ability to use any of these executors pretty easily without kind of worrying too much about configuration. So once these are kind of created, what you'll get back is some outputs. And these outputs are kind of like this, like how we instantiated those executors, it just gives it to you pretty much right away. So you can just copy and paste it and just use it. But going back to the example here, so among one of those outputs is going to give you what URL like your remote Covalent is living in. So you could just go ahead and like access it. Gonna make sure my URL's correct here. So I guess I'm probably gonna have to provision this. Let me see. Okay, so I'm just going to rename kind of what this is. Okay, gotcha. So yeah, I just have to define an SSH key here so I can use it. Sweet. So seems that I think the remote Covalent is kind of down, so I'm just gonna have to kind of create a new one. So I can just do that pretty easily though. Sweet. So I can then just provision all this infrastructure. So while that's kind of happening, I'll kind of continue here. So this should be kind of creating all the resources here. So pretty much the rest here is just, so since this is now Covalent, it will be running remotely. One thing we have to make sure is that we have all the dependencies defined. So again, whichever task you're going to use that executes remotely, you're going to have to determine the dependencies and add a decorator to it. So for when you're using Covalent with self-hosted, you don't have to have all those configuration values. You can just say AWS batch whenever you want to use AWS batch. It's already pre-configured, so it's a lot simpler to work with self-hosted here. So that's going to take a little bit to create, so pretty much just have one example using the support vector machine training, but just on self-hosted Covalent. So once this kind of boots up, we can kind of continue with that. But I think this is probably a good time to maybe show an example with just using PennyLane with a quantum circuit. So yeah, I think my colleague Ara will show a quick example. Do you want to
I'll do this one.
Okay, yes, sounds good.
Hi, everyone, I'm Ara. So down here, I'll just show you a quick example using Qiskit, PennyLane, and Covalent at the same time. So we're just going to do a really sort of trivial computation, which is to get estimates for the expectation value of this operator from this circuit in two different ways, and then we'll compare the differences that we get. So you can see I'm importing Covalent up here, along with all the other stuff that I need. I'm defining the two backends I'll use. So my PennyLane device is the local simulator for AWS Bracket. And then for the Qiskit, I'll just use the air simulator backend, the state vector simulator, with the same number of shots, of course. Right, so the workflow definition is sort of apparent from the code, right? You can see I have 3 electrons up here, each of which is a granular task that I want to run. And at the very bottom, I have my lattice, which is going to define the workflow exactly. So if you just look through this very simple function, I have 2 lists that I'm populating. And I'm gonna loop through these tuples of angles right here, 5, one for the Z gate, one for the Y rotation gate. And then I'm going to run each of my functions up here that use Qiskit and PennyLane respectively to get that expectation value. Let's just run this cell. Is this the video? Andrew, could you give me a hand here? Sorry. I just like to run the cell, but I can't seem to.
Okay. So yeah, so we'll install kind of some of the dependencies that you need. So this is just Qiskit, PennyLane, and the Amazon Bracket PennyLane plugin. And then we can just run the workflow. So right now we're just running it locally. So you should just be able to see it on your browser. I guess that worked pretty fast. So yeah, so that should be it.
Yeah, so you can see it's a little bit unfortunately arranged, but I can use some tools here in the UI to make that more clear. So let's arrange it the other way. So here's what's happening, right? I'm getting 4 values from each of the from PennyLane and Qiskit. I'm running each of those electrons 4 times. And what we're showcasing here really is how easily Covalent lets you parallelize this sort of thing. So in my script, I have just a simple loop that's marked as my lattice, and it's calling the functions that I marked as my electrons. And in Covalent, when it runs, when you actually dispatch the lattice, it understands that, for instance, these 8 tasks are completely independent and they feed into a list, and then both those lists independently feed into my final mean square error calculation, right? And so that's exactly what happens. And it happened very, very quickly. I will show you guys one more slightly less trivial example in just a minute. Okay. I guess you have to stop sharing first,
Yeah.
right? Yeah.
I can share it.
There we are. All right, so here I've taken some code from the Qiskit documentation and used Covalent just to, again, parallelize it very efficiently. I'll go over really quickly what's happening here just from the original doc page. So this is an implementation of VQE, which is the variational quantum eigensolver. So that's a NISQ-friendly method for optimization. I'll just scroll down real quick and talk about the problem here. So what we're doing is we're finding the ground state energy of the H2 molecule. So that's just 2 hydrogen atoms, depending on the bond length between them. And it's going to generate a plot that will look, I assume, familiar to at least some people here. In the example we have at hand, right, the code's just implemented in this very simple way. It just runs at the first indent level, and they're using 1 length for the atomic distance here. So there's a number of steps here, which we can identify. So first, we're generating the Hamiltonian for the molecule, and then creating the optimization problem, some conversions of the operator, and eventually the heavy lifting is done down here. So this uses the session primitive from Qiskit's IBM runtime. So inside here, what's happening, right? We have 2 functions, evaluate expectation and callback. We can ignore the second one. So in here, we are using the estimator primitive just to run the circuit on whatever backend is specified. In this case, it's the IBM Chasm simulator. Okay, and there's also a plot at the very end. So what you're seeing here is just the optimization succeeding to find the ground state energy. So the red line is just the exact solution, and then you can see the VQE solution converging towards it. Okay, so that's straightforward enough. So with Covalent, I can do the same thing at, I can run a bunch of different points at in about as much time as it takes to do one, because everything will be dispatched asynchronously and parallelly. And so as before, the first step to doing this is, well, for one, I have my IBM stuff set up. So I went to ibmquantum.com and I got myself an access token, which is free. And this function is going to grab that from my environment. But moving on to the actual experiment. So here I have electrons corresponding to those tasks that we saw in the original script, right? So a function that'll make my Hamiltonian for me. I have another one that does the exact solution, and I have a last one that does the VQE solution. So I also have my plot. Yes, let's not forget, this is going to be a different plot, by the way. So finally, the workflow, the CT.lattice. Again, very, very easy to write, right? So I make my 2 lists. I construct my Hamiltonian for each distance. I grab the exact solution. I grab the VQE solution. So when I call this, we'll be using, again, the Chasm simulator, right? Because the session primitive will dispatch that to IBM. And then in the very end, we can grab all that and plot it. So this one I will not do live because it's going to take like 15 minutes to run, but I will show you what the completed result looks like. So a much bigger transport graph in this case, right? And you can see that Covalent, again, traced out all the interdependencies between these functions. So you don't need to worry about actually doing this manually in any way. You just write your simple loop. You have your electrons, you have your lattice, and Covalent will do the rest of the work. So in this case, We can look at each electron. So here's one of the calls to construct the Hamiltonian, and we can see where it's being used. It's being used once for the VQE solution and once for the exact solution. And eventually we'll compile our two lists over here, and we come out to the plot. By the way, the UI will also show you a bunch of other useful information, like the runtime. So it's in fact 13 minutes, not 15, but still I won't write it right now. And so what have we done, right? We took like a really sort of a scientist's implementation of this code, and we just cleaned it up a little bit by putting stuff into functions, and now we have a fully scalable workflow, right? And it was fairly simple to do. We just have to use these decorators in addition to functionalizing stuff. Just to finish off, I'll show you what the result is. So I assume we've all seen this, something like this before, if you've taken well, maybe not, but anyways, here's the exact energy in blue, right? And then the VQ estimate, which is pretty good up until around 1.1 angstroms or so, where it starts to diverge. Of course, if I want to rerun this, that's really easy to do. I just go back. I have my maximum iterations variable. I can just make that into 80. Obviously, that will use, like, you're going to submit 80 jobs per optimization routine to CHASM this time, so it'll be a little bit longer, but that's all it takes. So if I just change that to 80, and now I can rerun the script, and I have my whole workflow intact, and it's fully reproducible. Of course, I can also go back and look at anything I've done in the past, just like I used to show you guys. Okay. All right, well, thank you very much.
Thanks, Sarah. Just kind of wrapping up here. So I understand that we were trying to show how to do self-hosted deployment with Covalent, but you know, there was kind of some issues there. So I have a video that I'll try to share through like Google Drive. So if anybody wants to kind of go through that and see that, you should be able to. But I guess we'll kind of stop for questions here that you might have about Covalent, or yeah, just questions for us. So yeah, does anyone have any questions? Cool. Okay, well, yeah. Oh, yeah.
Just wondering what software we need to install to take on this challenge.
Yeah, for sure. So you'll just need to have Python, and if you want to use AWS executors, I recommend getting a CLI tool, AWS CLI.
Is that required for the challenge?
I mean, so it will probably factor. The only place that will factor into probably is like there's the judging criteria also says about scalability. So scalability being, you know, like, can a lot of people use your application? And if it's just hosted on your computer, I would say that's not a lot of scale. But if you end up leveraging AWS as for the cloud, you can get to more scale. So I would say that's probably higher. It affects probably a little bit the score. The other, if you do want to use AWS, you need to have Terraform as well installed. Yeah, but that's pretty much it. We have this notebook as well in the. I don't think it's gone live yet. The iQuHACK challenge page, but this will be on there. I'll try to include the video as well in the challenge page as well. But yeah, thanks a lot. Unless there's any other questions, I think we're good to wrap up. Because yeah.
Because I'm not an expert, but could we choose to run GCP in the backend instead of AWS?
Oh, that's a great question. So it's on the roadmap for us, but right now we have AWS executors. Yeah.
We have them use AWS, right?
Right now, if you want to use those remote executors, yeah. Yeah.
Is it more open-based challenge or more?
In what sense?
In terms of like, more creative design, like multiple solutions, or
Oh, yeah, it's quite open-ended. Like, so if we're talking about the challenge, so it really is just if you can find a practical usage of quantum. So it doesn't have to be like speed, like you don't have to have speed ups necessarily. It can be inefficient, but just anything, any kind of, let's say you can think of it as like, can you publish out your tool tomorrow and people would start using it, but it uses an aspect of quantum. And that's kind of what we want to see, like a lot of practical applications. Yeah. Cool. Any other questions? All right, going once. All right, cool. Well, thanks a lot for listening to us, and yeah, we're looking forward to the submissions for the challenges. Thank you. Oh, and start a repo on GitHub if you can, because that, yeah, we love you guys if you do that. Awesome. Sure.